Today, let us discuss about a topic called as sampling and how to convert continuous time signal to discrete time signals. And this job is done by a theorem called as sampling theorem. So, sampling is a process of converting continuous time signal to discrete time signal. Using a process called as reconstruction, we can convert back discrete time signal to continuous time signal. What is the need for sampling? Why do you require? We all know that all real-time signals are analog in nature, like image, text, video, and so on. And all signal processors are digital in nature. Digital signal process has a lot of advantages compared to analog. So we require a technique where we can convert analog signal to digital, and one of the steps in that is called as sampling, followed by quantization and encoding. Put together, it can be called as analog to digital converter. So in order to convert continuous time signal to discrete, sampling is required. So let us consider a block diagram. I have a continuous time signal such as voice. Using a process called as sampling, I'll convert them to discrete. Discrete signal will have many levels. I want to convert them to digital to have two levels. So I'll opt for a concept called as encoding. This digital data available after sampling, quantization and encoding will be passed to digital signal processor, where we can implement lot of signal processing algorithm. Before giving to the destination, I must convert back this digital data to analog. So I'll use digital to analog converter to get back continuous time signal. In this, I have considered three analog signals or continuous time signals, x1 of t, x2 of t and x3 of t. And all these three signals are not same, they are different. Once you perform sampling, replace t by n into t, where n stands for discrete time interval and capital T stands for sampling interval, that is distance between two consecutive samples. To understand how continuous time signal can be converted to digital or discrete, there are many techniques in sampling theorem called as ideal sampling, practical sampling. In ideal sampling, the sampling function that we use is impulse train. With respect to this diagram, I have considered an analog signal x of t, multiplied this with an impulse train p of t to get a sampled version xp of t. When we observe this diagram, continuous time signal exists in all the time instance. When we multiply with impulse train, its signal is captured or allowed only at multiples of t, like 0, t, 2t, 3t and so on. In between 0 to t or t to 2t, the signal is not allowed. The sampled signal is obtained after multiplying an analog signal with impulse train, which is an ideal situation. Since impulse function is used to sample a continuous time signal, such a technique is called as impulse sampling. Again, same approach, x of t is an analog signal multiplied with p of t pulse to get a sampled version called as xp of t. Mathematically, sampling can be obtained by using a product modulator or a multiplier which takes analog signal with impulse train. Let us apply Fourier transform on both sides. Xp of j omega, frequency domain representation of sample signal, is equal to 1 by 2 pi x of j omega convolved with p of j omega, as we all know that multiplication in time domain is convolution in frequency domain, where p of t that we have taken as an impulse train existing from minus infinity to plus infinity at regular intervals of nt. Again, I have taken one more waveform to illustrate this. X of t analog signal. Second diagram, impulse train available at multiples of t, that is sampling interval, multiply x of t with p of t to get a sampled version xp of t. In order to understand frequency domain representations, x of t was analog signal we have taken. Applying Fourier transform, I have got x of j omega. P of t is a impulse train. Apply Fourier series to get an answer p of j omega. And xp of t is a sampled version of x of t. In frequency domain, applying Fourier transform looks like xp of j omega. When you observe xp of j omega, the spectral replicas x of j omega is shifted by omega s, where omega s stands for sampling frequency. And these terms are available from minus infinity to plus infinity, which implies that sampling in time domain introduces periodicity in frequency domain. Let us understand this concept with respect to a spectral analysis. I have considered an analog signal band limited to omega m radians, means existing from 0 to omega m. The second function, impulse function in frequency domain, has non-zero values at 0 plus or minus n omega s, where omega s is the sampling frequency in the units of radians per second. Now I want to convolve these two, that is x of j omega convolved with p of j omega. As we all know that any signal convolved with impulse is equivalent to shifting. So x of j omega multiplied with the delta f, delta omega, you will get the same spectra from minus omega m to plus omega m. Second, x of j omega convolved with delta omega minus omega s is equivalent to shifting the complete message spectrum around omega s, similarly around 2 omega s, and so on till infinity. The sampling in time domain has introduced periodicity in frequency domain, and only the required spectra is from minus omega m to plus omega, and remaining spectral components are replicas of the original message signal, which implies that sampling in time domain has introduced periodicity. The periodicity is with respect to omega s radians per second. Selection of omega s is very important, because if the second replica overlaps with the original one, overlapping of higher frequency components occurs, causing a problem called as aliasing effect. In order to avoid aliasing, the proper selection of omega s is important, that is, choose omega s greater than 2 times omega m, and this condition is called as Nyquist criteria. If you don't satisfy Nyquist criteria, overlapping of higher frequency components takes place and aliasing occurs, hence higher frequency components gets distorted. Conclusion of sampling theorem. If x of t is band limited to minus omega m to plus omega, a band limited signal, and this signal can be uniquely represented by its samples taken at regular intervals of time, that is x of nt can be converted to discrete time signal x of nt, provided the sampling rate chosen omega s is greater than or equal to twice omega m. If omega s is greater than 2 omega m, it is called as oversampling. If omega s is equal to 2 omega m, it's called as exact sampling or Nyquist sampling. And if omega s is less than 2 omega m, and this situation is called as undersampling.